So I'm also in the virtual platform camp along with Johannes here on the panel, and I also used the standard template. Okay, so we know a little bit about Accelera through the course of the day and the activities that are going on there for System C. And it really starts like this. We've got a problem, we innovate, we figure out how to deal with the problem, and then we realize that it needs to become bigger and broader, and we collaborate with others. That becomes fruitful when we get to standardization, and then of course we've got interoperability. And this is kind of the area where Accelera plays. A lot of innovation does continue once there are a starting point that's provided within the working groups there. And what's really important, Johannes talked about, well, in 1999 we had a language and we thought, well, we're done, let's sit back and enjoy life. What really happens is it's the next set of problems that come about. So we have seen TLM was a major milestone, and we now see that the standard's getting pulled in lots of directions to support a lot of different needs. So analog mixed signal, the configuration control and inspection, ongoing improvements to the language, support for multi-threaded host, for example. Of course, the synthesis work and the verification activities that are going, a lot of things are happening kind of in this continuous cycle. Not only is it continuous and building upon the previous generation, there's multiple kind of lanes in that racetrack around the System C standard. The good thing is that each advance spurs broader adoption, and TLM2 is a very strong case in point for that. We saw the tools jump right on it. We saw users coming to conferences and talking about what they were able to do with it, and it was a really good springboard for the standard. And of course, we do take it to IEEE for a rev every 5 years. So we're kind of focused in this panel talking about high-level synthesis and virtual platform, all being on System C. And so, yeah, they're the same universe, but they really are worlds apart. And Johannes referred to the fact that people in the VP camp really are squeezing every cycle out of their simulations that they can. The goal there is system software execution, demands high speed. We're wanting to boot operating systems in seconds. What you do there is you model as abstractly as you can the software interface of the hardware, and employ as many speed-up techniques as you can to get there. And the high-level synthesis domain, in my simplified view, Mike would come over and beat on me when he sees what I've done here with the code, but it's about describing the hardware, right? We talked about accuracy, accurately describing the hardware so that we can feed into a synthesis engine. So I've got these columns here showing us just a little snippet to give you a sense for this. So if we're talking about a countdown timer, some pseudocode for it. In the HLS world, it's at every edge of the clock. I'm going to decrement my counter as long as I'm enabled. And when I hit 0, I'm going to fire an interrupt. Straightforward. In the VP world, it's abstracted in the sense that once we're all set up, what we do is we determine when the VP is going to time out. So it's maybe, you know, it's 1,000 ticks times 25 nanosecond period, and I schedule that out in the future, and then I just sit back and I relax. And now that HLS model sitting there cranking away every clock cycle, trying to figure out how to take that register value down by 1 notch, and the VP version just sitting there waiting for to be notified that we're going to wake up. In terms of speed, you know, we're talking about, depending upon the size of the count here, the count value, but we're, you know, 1,000. Order of 1,000 faster if it's 1,000 count value or higher. The challenge here is, though, that we have to deal with complexities. We have to deal with the dynamic things that come into the simulation. So if my counter value changes, if my enable changes, if my clock frequency changes along the way, I've got to stop. I've got to figure out how far along I have come. I've got to recalculate how far I'm going to go. I've got to cancel my previous event. I've got to schedule my new event. Now I'm off and running again. As well, if I want to service a read to my counter register, it's not being updated every clock cycle. I've got to stop, figure out how far along I've come. At that point, I may as well go ahead and just recalculate everything that's going on, update all the values that I can, and then respond with the appropriate value to the software. So yeah, that's really fast, but throw that at a synthesis engine and we're going to have a hard time. So that's kind of the two different worlds that we're talking about here. Serving both of these well, right, and well to me is better than 2x performance penalty, you know, is a challenge today. So stepping back from that problem, I want to kind of have some discussion in the panel about what we can do from a standards point of view. And I think that one of the things that we need to look at is a more holistic perspective on what we do with the standards. So Karen Pieper talked earlier about the fact that in Accelera we do have this council that's all the chairs of the working groups come together and they talk about looking at things from a holistic point of view, but I do think that there's lots of room for improving upon that. So a couple of examples. One is configuration parameters. In the virtual platform world, all that we really want to know about a configuration parameter is really, does it need to be set before elaboration or after? In other words, is it going to affect my module hierarchy or not? That's really all that I care about. The HLS world, of course, also cares about that, but maybe they also want to understand whether things are purely simulation artifacts and they aren't applicable to an implementation. Or things that are going to end up in a fuse. Maybe there's another level of detail there that we need to take into account when we define what a standard System C configuration parameter is. Next one is registers. So in the virtual platform world, we talked about through the course of the day being able to have debug capabilities standardized for our System C models. And a backdoor API is sufficient for that. If I can come in through a backdoor as a tool and get the details of what a register structure is and what its values are and some descriptive information and pull that out, present that to the user, that user is able to do debug effectively. But in the HLS world, we need to be able to infer a register, and if we've got different models using different implementations of registers, that becomes difficult. We certainly couldn't imagine a system Verilog world where register wasn't part of the language. So forward-looking, maybe there are more additional things that we can do. You know, how can we get to the point where we can get something that works optimally in both domains from a single description? Now, whether that's some improvements to the language or some building blocks that we can come up with is yet to be seen, but I think that we want to step back and kind of start thinking about how can we do that. So real quick then, virtual platforms are real, but they're not real enough today. There's not enough compelling value that everybody is using them. Accelera is driving System C to the next level with standards. And holy grail for us today is this single model serving both virtual platform and high-level synthesis. And we're going to have to come up with doing things better to take us to that next level.
Thank you, Trevor.
Yeah, you bet.
And with that, I think you probably have gotten enough background into both the HLS world and the virtual platform world. So I would like to invite our audience to direct their questions to the panelists. So, Shishpal.
Actually, I have 3 questions. Let me start.
3, okay.
Microphone.
Here you go.
My first question is, what's the speed-up difference between virtual prototyping versus emulation?
I guess I can answer that.
Okay.
So virtual prototypes typically run in the 50 to 100 megahertz range, and emulation runs between 1 and 10 megahertz.
So like a
very, very rough ranges. Action mileage varies.
The second question was, in many companies, there's probably already pre-existing HDL, and there are certain tools that convert HDL back into some C models, and then we use that to get speed up if needed. Do you have any comments about that sort of an approach versus starting the other way around for HLS guys?
I can make one comment there. I mean, yes, maybe those tools work in the short term, but if you think about what they're doing, they're compiling the code, and that's what EDA simulators do. So unless they're changing the abstraction in the model, they're really not going to be able to speed up the simulation in the long term. You have to take something out in order to get it faster.
I think you mean something like the carbon design tools that
Yeah,
basically
for example,
take
so
the HDL out and convert into sequential.
So if it's the same abstraction, theoretically it should simulate at the same performance. You would need to do something else to get it to really go faster. Now, maybe in the short term, Carbon has some fancy optimization that can do it, but there's no reason you couldn't do that inside a commercial EDA simulator.
Another comment I'd make is that structurally, an RTL model has a specific granularity of transaction. It gets the data in the chunk sizes that it gets it. And one of the things that you do often in virtual platforms is expand that size of data that's presented to the model in order to have less transactions and less process switching and get more speed. You can't really do that if you start from an already completed implementation.
This is your full frame versus a pixel example.
Right, exactly. So you can't really attack that problem if you start with a fully finished RTL as the source. If you start with a high-level model and you want to attack that problem, you can do some things. You end up with some conditional stuff in your code. So the model you're running the virtual platform is now a little bit farther from the model that you're actually using to feed to the tool to do an implementation. And people make those trade-offs.
Okay.
Maybe another way to answer that is from the 12 examples in the book that I mentioned, also 0 had a translated model as part of the virtual prototype because it's not fast enough.
My last question is there a way to refine or add incrementally more information in System C? It appears that you said the pure virtual prototyping platform for speed is kind of incompatible with the model for high-level synthesis. So is there a way to kind of incrementally add information while still maintaining the same look and feel of the original model that one would have developed for performance, for instance?
For some designs, yes. So now you really have to start to cut it apart into, typically high-level synthesis is used in hardware accelerators like image processing or wireless or something like that. There, it's a very somewhat simple interface between the hardware and the software. And there, it's more practical and easier to do that kind of refinement. If you're talking about something that's very tightly coupled into the processor or the processor itself, I think that'd be really hard to do.
I think that's true, and I think the extent to which you want to, it's a high priority for you to keep that original style, it gets harder and harder. As a general rule, I think that starting with the virtual platform code and attempting to turn that into a high-level synthesis model, not the best approach. So building a high-level synthesis model and modifying that with enhancements to bypass some things, to change the granularity of transactions, some other stuff like that, to increase the speed of it in the use as a virtual platform model. You can get some distance that way, and you actually get some distance in speed, whereas coming the other way, you never quite get to something synthesizable.
Okay, so which parts of VP could be synthesized with HLS today?
I sort of alluded to that a second ago.
Which parts?
So really what you're talking about are we call them the hardware accelerators, right? So the image processing subsystem, the graphics subsystem, the wireless baseband. If you're talking about a cell phone, right? Think about, you have your core ARM processor probably. You have all these peripheral subsystems with their own processors. Everything around that subsystem processor can be done in high-level synthesis.
And the stuff next to the sensor.
Yeah, and the stuff, whatever this, yeah.
Okay. If there's a need for speed to validate the system, I know it sounds like the virtual prototyping system allows software to be done earlier, and if you have a parallel model, you maybe get to implementation of an algorithm faster. But where does the FPGA prototyping come in? Does it solve some of that speed to boost from your 1 megahertz, 50 megahertz, maybe take you to 200 megahertz?
So I can try to crack on that. Of course, we do offer FPGA prototyping. The biggest need for FPGA prototyping comes in when you want to connect something to the real world. You cannot really connect a virtual prototype to the real world if you do interface software validation. So when you want to connect something to the real world, you need a PHY card, you need a PHY interface chip, and then you can connect an FPGA prototype with the real world and do real validation. And that's what customers do. Besides, customers, of course, say, just using FPGA prototyping as the traditional method if they're not convinced to shift to virtual prototyping.
And a third use, I think, is people use FPGA prototyping to prove that they can build it. If they have to get some next level of investment or next level of approval for their project. They will prove, okay, we can build something that does what our specification says.
Two questions. I think the first one's quick. Trevor, you alluded to this. Are there any steps that you see taking an HLS model to virtual platform model? I kind of came away with no, that they are two different things, but.
I think they're really two different beasts today. I think Mike's right. If you have the proper forethought and a methodology in place, you can get to a point where you can get a lot of commonality. But I think that today's state of the art requires that you go down that path with a willingness to concede some performance in the virtual platform space. And 2x, doesn't sound like a whole lot, but I can tell you that the software teams who are booting operating systems and trying to get early software development done, you take them back 2x and they scream like squashed cats.
Right. And unfortunately, it's the case that having, not entirely true, but generally having one element, which is a lot slower, slows everything down.
Yeah.
If this is only maybe 10% of it and it's twice as slow, it's a lot closer to the whole thing being twice as slow than it is to it being just 10% slower.
Yeah, that's true.
And then the second one, I remember years ago at DAC, prior to acquisition, Cohere, the Vantage, the virtual platforms, booting Linux, all this stuff. And I remember coming away thinking, yeah, this is really cool, it's really fast. I don't think I could code this. Is there any book that teaches somebody how to code a virtual platform, or do you just, maybe you like this answer better, or you just come to you and buy it?
Not in System Verilog.
Oh, well, I'm talking System C. I'm talking System C now.
Yeah, so System C, I think there's two levels.
Taking away from System Verilog.
So first of all, you have to see how much System C knowledge do you need. And of course, as a tool vendor, we try to take away all the heavy lifting from you to the extent we can, like the infrastructure, the plumbing, the interfaces. And then you have to be able to code for speed, which is an art in itself. And those are things we teach. No books yet. Can't recommend a book yet. So it's mostly things we do directly with customers.
Yeah, there are some books out there that provide the basics, of course, with TLM. So System C from the ground up, for example, is a pretty popular book in that space, but it's very generic. To really get to doing good modeling, you're going to have a good modeling methodology, and you got to either have one or you got to work with an EDA partner, leverage theirs.
How important is to include analog in virtual prototyping? And is System C AMS a promising direction?
I would start by saying opinions differ. But what System C AMS is aimed at is doing just that, is taking, connecting the analog computations either to model the analog behavior of the circuit or the analog behavior of the real world, and incorporate that in your SoC model, your virtual platform. As opposed to for modeling transistors and that kind of more traditional analog stuff. And the people that are using it are pretty high on it.
Yeah, my comment is analog is of course important, certainly in areas like automotive, it's extremely important, because you cannot really develop a microcontroller software if you don't model the brake itself or the engine itself. So customers will typically use whatever they have as a description of their environment, and that has to connect to a virtual prototype, probably at the tool level. System C AMS is an interesting language standardization, and we'll see some customers are using that, and of course we need to help them to integrate System C AMS defined environments into a virtual prototype. So it's one of many methods.
Have you seen any success in these 12 systems that were put together of, I guess, IP interoperability, stuff being delivered from third parties and integrated together, or are all these just a single user's system that they've built up with all their own IP?
No, for the most part, they're all based on standard System C models that have been developed by third parties. Most importantly, ARM, of course, as the #1 processor IP provider Many of these systems were ARM-based designs. Some of them are specialized MCUs, where the semiconductor vendor would basically model again the System C TLM2 standard compliant model. So System C TLM 2.0 was really the watershed when reuse of models and interoperability became a non-issue.
I'd like to point out on the high-level synthesis side that is more common. For example, Google has open source VP9 and they collaborate with other companies. So they did a collaboration with VeriSilicon and they both contributed to the code and did joint development between here and China. And were able to produce a pretty nice piece of IP. So, I mean, it is possible to get that to that point if you have a strong tool, standard, whatever, at the base of this.
So I'm going to ask one question that Cliff actually brought forward in our discussions we were having about invigorating EDA, so to say, which was make System Verilog a subset of System C. So I would like to get comments from each one of you as to what you think of it, especially given comment from Mike that if you can actually speed up the reverse compilation, you can actually speed it up even in the software algorithms themselves, and perhaps get the speed of the prototypes back into the virtual prototypes. That basically bridge the gap between HLS and virtual prototype.
So first I'll offer my chair to Cliff to come and answer this question because I think it's directed at him. But I think what he was commenting on was a wish to be able to define a subset or a coding style of System Verilog where you could write high-level System Verilog and know that it could be presumably machine translated into System C for use in virtual platforms, for use in high-level synthesis, for use in the kinds of places where System C is prevalent. Was that where you were headed? I have never thought of doing that, but that seems like that might be a possible thing to do, and might have some syntactic benefits, right? There's syntactic benefits of System Verilog over System C in terms of the number of characters you have to write and the number of times you have to write the same thing. And so for those kind of benefits, I think that might make sense.
Right. But, okay, I'll take the other side then. But the thing that I see in System Verilog is that it does not have the same memory infrastructure control pointers sorts of things that you have with C++. So the stuff we do with template specialization in particular is well above and beyond anything we have in Verilog or System Verilog. So yes, if you can bring me pointers and dynamic memory allocation and templates and pointer specialization, if you can bring that into the Verilog world, it probably would make sense. But at the moment, we've all got a lot invested in System C, and it seems like a shorter path to bring the good stuff from System Verilog over versus merging the languages or trying to go back to System Verilog.
The other perspective I want to offer is who is actually writing models for a virtual prototype. When we surveyed the customers that have implemented it, the customers that were not successful were those companies that tried to use hardware designers and teach them how to model in System C at an abstract level. The companies that were very successful and are still very successful are the companies that decided, let's take a population of our software developers and teach them how to read a hardware spec and then write a model. And that is inherently more successful because they understand what they can do with the modeling constructs after some time. It takes some time of learning, but then they're very capable of writing a model which is very efficient, which exactly serves the purpose of the software programmer, which is to see certain effects of the hardware, of the specification that are relevant for the software development.
And that sounds right to me, and that's pretty much the opposite of where we have success in taking existing people in the hardware world and turning them into successful high-level synthesis designers. The most successful high-level synthesis designers are folks who have RTL experience, and there's some stuff they need to unlearn. You don't have to do this part, you do still have to do that part. And there's a new language involved, and so there's some learning in there. But we have the most success teaching RTL designers to be high-level synthesis designers rather than trying to teach software designers to do.
Yeah,
I'm not sure quite why that is, but I think
Yeah.
that's very interesting that those do
That's 15 years to
flip
learn
that
that.
way.
Yeah, I think the languages probably are very powerful, independent, and putting them together might make a mess. Coupled with the fact that today there is really good support for being able to take and mix and match these, right? At the HDL simulator level across the industry, it's pretty seamless to be able to mix and match. So I would say leave them separate, couple them together when needed.
But if I could write the module structure and the connectivity in System Verilog and have that automagically become System C that I then put the behaviors in,
I mean,
I think that would be nice.
But why not
I'm
do
not
that-
sure quite it actually fits together into a whole.
But I think that's also
But
here
I think
today
it's
with
the
IP
idea.
exact, right? You define your module structure and your connectivity in IP exact, and you get a generator that
Generate
produces
whatever you need.
System Verilog.
Sure, that's another approach.
Yeah, that's the norm, I think, today. Throw in some system RDL with it.
That's why we have System C. It's because Verilog and VHDL wasn't enough trouble.
But, I mean, mere humans can't write anything in IP exact.
Any other questions for our panelists? Okay. Well, then I would like to thank all the audience and our distinguished panelists for this great discussion. Thank you very much for coming. Appreciate it.
I think we get a 20-minute break.